Hi, and welcome to this presentation on our recent paper entitled Gradient and Shim Pre-emphasis by Inversion of a Linear Time-Invariant System Model. My name is Johanna Vannesjo, and I will give you a brief introduction of the paper. The work has been conducted at the Institute for Biomedical Engineering at ETH Zurich and University of Zurich. To begin with, we want to characterize the dynamic behavior of our gradient and shim system, and to do this we model the system as linear and time invariant. Such a system can be completely described by its impulse response function, and any output is given by the input convolved with the impulse response. In the frequency domain, this corresponds to a multiplication of the input with the transfer function. To determine the shim impulse response function, or the SURF as we call it, we feed a known input pulse to the system and measure the field response. To fully cover the desired bandwidth in the characterization, we probe the system with a frequency swept pulse, or a chirp. Here showing the input chirp and the measured field response in one of the shim channels. We can also listen to the acoustic response of the system while playing out the chirp pulse on one of the shim channels. With the measured field response, we can calculate the SURF, here shown in the frequency domain for the XY shim channel. There are many interesting features to look at in the measured SURF. First, if we zoom in around the center, we see that there is a sharp peak around DC. This corresponds to long-living eddy currents running on the heat shield of the cryostat. And if we look at the effects of the long-living eddy currents in the time domain, here for a series of shim steps, we see how the shim field slowly converges to the desired levels. Another interesting feature to look at are quite sharp peaks occurring in the range of a few hundred hertz up to a couple of kilohertz, and these correspond to mechanical resonances of the system. Looking in the time domain at the effect on the field of the mechanical resonances, we see that we have oscillations for tenths of milliseconds after a shim step. Here we are showing again the measured SURF at the top and the corresponding time domain step response of the system. As we have seen, the response of the system is not ideal if we want to use the shim system dynamically. Rather, we would like the system response to look more something like this: a smooth transfer function in the frequency domain, where the speed of the convergence of the step response depends on the bandwidth of the transfer function. So one generic approach to achieve such a system response is to pre-distort the input waveform by a pre-emphasis filter. To achieve the desired target response, the pre-emphasis filter should be made up of the target system response multiplied by the inverse of the native system response. If we apply such pre-emphasis filters on our shim system, we achieve measured SURFs looking like in the lower plot here, and we can see that they very nicely resemble the corresponding target filters in the upper plot. But that is not the whole story. When we play out a pulse on the system, we do not only get a response in the desired field term, but we also get responses of undesired spatial field distribution, that is, cross-term responses. Here we are showing the self-term response of a third-order shim channel. And here is the response in the Y field term, the linear field term, to playing out a pulse in the same third-order shim channel. So to fully characterize the system, we need to determine one transfer function for each combination of input and output channels. This leaves us with a full matrix of transfer functions. Here we have the self-term responses of the different channels on the diagonal, and we can see that they vary widely in bandwidth and shape dependent on the channel. But we also see that we have a whole range of cross-term responses, and they are particularly strong in a number of cases, as for example the Z-square shim channel coupling into the 0th order field term, and some third-order shims coupling into the linear field terms. To compensate for the cross-term responses in a pre-emphasis approach, we would need to drive the corresponding shim channels to actively cancel out the induced cross-term fields. The compensation will in itself cause cross-term responses, and so forth. Luckily, it turns out that we can use the same approach as in the single channel case also for the cross-term pre-emphasis filter, but in this case using matrix notation. So now our pre-emphasis is a whole matrix of filters, constituted of the matrix inverse of the native system response matrix, multiplied with a matrix of target filters. If we implement the full matrix pre-emphasis on our gradient and shim system and remeasure the system response, we get these results. Now we see that the self-term responses all nicely follow the target filter behavior, and the cross-term responses are almost completely suppressed. Looking at the series of shim steps in the time domain, with and without pre-emphasis, we can see the impact this would have on dynamic shim updating. Zooming in more closely on the X channel, we see that without pre-emphasis, in dark blue, the response deviates strongly from the target, in this case due to cross-terms. If we only perform the self-term pre-emphasis, in light blue, the deviation is actually even larger, whereas with full matrix pre-emphasis, in red, we get a response that nicely follows the target shim steps. If we instead look at one of the second-order shim channels, we here see that the self-term pre-emphasis improves the response, but we still have quite some oscillations after the first shim step. With matrix pre-emphasis, most of these oscillations are suppressed, indicating that they were cross-term responses to steps in other shim channels. The full matrix pre-emphasis approach enables us to perform slice-wise dynamic shimming with a higher-order shim system, shown here for single-shot EPI in a phantom. We see that without pre-emphasis, we get large geometric distortion because we're not actually achieving the desired shim fields, whereas with full matrix pre-emphasis, we get good geometric fidelity. This can also be implemented in vivo, here showing single-shot EPI of the brain at 7 Tesla, with slice-wise dynamic shimming with and without pre-emphasis. Only in the case of full matrix pre-emphasis do we get the improvement in geometric fidelity that we target with the slice-wise shimming. Thank you for listening to this presentation, and please do get in touch if you have any questions.